All right, let's be real for a second. AP Physics mechanics problems, they can get complicated and fast. But what if I told you there's one simple sketch, one single diagram, that is literally the key to unlocking almost every single one of them? Well, today we're going to absolutely master it. So, what is this secret weapon? This magic key? You guessed it, it's the free body diagram. Look, getting this right means you are well on your way to crushing the mechanics part of your exam. But get it wrong, and trust me, even the easiest problem feels impossible. It is that critical. Okay, so here's our game plan. We're going to kick things off with why this diagram is such a big deal. Then we'll get into the nitty-gritty of isolating an object. I'm going to give you a foolproof 4-step method that you can always rely on. We'll put it into practice, and then, super important, we'll cover the common traps that trip people up. By the end of this, you'll see exactly why this is the key to all of mechanics. All right, section 1, the most important diagram. So why all the hype about a simple sketch? Well, because the free body diagram isn't just a sketch. Think of it as your universal translator. It takes a messy, real-world situation, with blocks and ropes and tables, and translates it into the clean, simple language of physics, the language of Newton's laws. You can't even begin to use that famous equation sigma F equals ma until you know what sigma F actually is. This diagram? This is how you figure that out. It's step 1, and honestly, it's the most important step you'll take. Okay, so that brings us to the core concept here, isolating the object. The whole magic of a free body diagram comes down to this one powerful idea: isolation. See, to really understand what's happening, we have to put our blinders on and focus on just one single object at a time. We have to pretend everything else in the universe doesn't exist for a moment. And here it is, the official textbook definition. A free body diagram, or FBD, is a super simplified diagram. You take your object, your body, and you represent it as just a single dot. Then, and this is the important part, you show all the external force vectors that are acting on that object. The two phrases you have to burn into your brain are single object and forces acting on it. That's the whole game. I've got a great analogy for you here. Think of it like you're a stage director. When you draw an FBD, you're shining a big, bright spotlight on your main character, the object. Everything else, the table it's sitting on, the air in the room, the person who pushed it, all of that fades into complete darkness. The only things we can see are the forces that actually reach out from that darkness and touch the object in our spotlight. That's it. Okay, that might still feel a little abstract, right? So let's make it super concrete. I'm about to give you a foolproof 4-step method. This is the process you can lean on every single time, especially when the pressure is on during an exam. You follow these steps, you're gonna get it right, period. All right, you ready? Step 1, isolate. You mentally pick up your object and pull it away from everything else. Step 2, represent. You take that object and just replace it with a single dot. Why? It gets rid of all the noise, all the clutter. Step 3, identify. Now you play detective. You find every single push or pull, every external force acting on that dot. And finally, step 4, draw and label. For each force you found, you draw an arrow starting from the dot, pointing in the right direction, and give it a name. Isolate, represent, identify, draw. That's your recipe for success. All right, enough theory. Let's put this method to the test and see it in action. We're going to build an FBD for the most classic physics problem of all time, a simple book resting on a table. So, picture this. You've got a book. It's just sitting there on a table, not moving, not doing anything exciting. Now, before we can even draw a dot, we have to make our first big decision. What is our object? What's in the spotlight? Well, it's pretty obvious here, right? We care about the forces on the book. Okay, time for our 4-step method. Steps 1 and 2, we can knock these out at the same time. First, we isolate the book. So in our minds, the table disappears, the room disappears, all gone. Second, we represent that book with a simple dot. Boom, done. See how easy that was? Now we're ready to find the forces. Okay, on to steps 3 and 4. Identify and draw. So let's think. What's the most obvious force acting on pretty much anything on Earth? You know it, it's gravity. The entire planet Earth is pulling this book downward. So we draw an arrow starting from our dot, pointing straight down. And we'll label it W for weight. You could also call it FG for force of gravity. Either one is fine. Now hold on a second. If gravity was the only force, what would the book be doing? It'd be falling, right? It would accelerate straight down through the table. But it's not. It's just sitting there. So something must be pushing back up, balancing out gravity. And what's touching the book? The table.
The table is pushing up on the book. We call this a contact force, and its special name is the normal force. Normal here just means perpendicular to the surface. So we draw another arrow, this time pointing straight up from our dot, and we label it N. And just like that, we're done. That's it. That's our complete, perfect free body diagram. We've taken a real thing and turned it into physics.
Okay, so knowing the right way to do it is awesome. But, and listen up, because this is huge, knowing what not to do is just as important. I want to talk about the common traps, the mistakes that I see students make over and over again on their exams. Let's make sure you don't fall into them. Here they are, the top 3 mistakes you need to avoid. Number 1, including internal forces. These are forces inside the object, like the molecules of the book holding each other together. We don't care about those. We only care about external pushes and pulls. Number 2, confusing action-reaction pairs. Remember Newton's third law? The book pushes on the table pushes on the book. Those forces go on different diagrams. You never, ever put an action-reaction pair on the same FBD. And number 3, this is the big one, including MA as a force. We're about to dive into that one.
Okay, look closely at this, because this is probably the single biggest mistake students make. On the left, you see what is absolutely 100% incorrect. They've got the real forces, weight down and normal force up, but then they've added this extra arrow, MA. You cannot do this. MA is not a force. It's not a push or a pull from some object. It's the result of the real forces. It's what happens because of the forces. The correct diagram, on the right, only shows the actual physical interactions. You draw that diagram first, then you use it to write your equation where the sum of those forces equals MA.
So let's bring it all home. We've gone through the steps, we've practiced, and we've looked at the traps to avoid. Why have we spent all this time on one little diagram? Because mastering this unlocks everything else in mechanics. It is the absolute key.
I love this quote because it's so true. The FBD isn't just a diagram, it's the blueprint for solving the problem. Think about it. You wouldn't try to build a house without a blueprint, right? It'd be chaos. It's the same in physics. Once you have a correct, clean FBD, your blueprint, writing the equations becomes almost mindless. You just look at your diagram and write, okay, all the up forces minus all the down forces equals MAY. The blueprint tells you exactly what to do. So mastering the free body diagram isn't really about getting good at drawing dots and arrows. It's about learning how to see the physics of a situation with total clarity. It's a tool that takes problems that seem messy and complicated and makes them simple and solvable. So now that you have this powerful blueprint in your toolbox, what are you ready to tackle? A block sliding down an incline? Pulleys and ropes? A car going around a banked curve? The sky's the limit. Now go get some practice.